Okay, well, happy Friday. It's week 5 Friday, so that's like halfway through our quarter. um, and it's also Data Fest weekend, which is exciting, right? Are you guys participating in Data Fest? Yes. Okay. So if you're participating in Data Fest, you'll automatically get a 3-day, 72-hour extension for the homework, which is due this coming Monday. So just somewhere in the homework when you turn it in, say you participated in Data Fest. If you want to include just the confirmation email that your team was selected or something, that's good enough. Okay. Yeah, I'll probably make a couple stops by Data Fest, so sometime this evening maybe, and then probably sometime tomorrow I'll show up as a quote unquote mentor. I don't know what. Basically, I think I just go around, and if you have questions about how to do something or just want to bounce some ideas off, there's several of us who are quote unquote designated mentors, and we're happy to offer our 2 cents of advice. It may or may not be good advice. Okay, we most on the people who are mentors haven't taken an extensive look at the data directly, so they probably don't know too much, but they can at least advise you on I guess what their thoughts and opinions. And of course, what you as a team decide to do is up to you. Anyway, today's lecture is a little bit of there's kind of 2 different topics, and we'll just kind of throw them together. And so, anyway, we'll take a look. So, and these slides aren't. They're fairly informal, so not. So anyway, I wanted to take a look at section 2.11 in the textbook. So I don't know if you guys have been reading your textbook or using it. So I think there's good stuff in the textbook. So one of the homework problems was doing regularized least squares, and it kind of worked through the derivation for that on page 36 of the textbook for finding the values to use for W hat when you're doing ridge regression. And then today we'll take a look at section 2.11. We've been kind of taking this maximum likelihood approach for discussing linear regression and how the solutions that we've arrived at regarding our parameter estimates, that's the result of modeling our data from a probabilistic perspective using Gaussian noise as or a normal distribution to model the noise that we see. And when we did that, it gave us a little bit of insight as far as information that we gain from the data, and how much information do we have about the parameters and things like that. And there's quite a few notes and derivations in the textbook, and I've kind of skipped over. If you want to read all of the derivations for this, you can look at page 85 in the textbook. But I just kind of wanted to cut to the end where we're looking at sigma squared nu, and it gives us this result. And I wanted to talk about what this is, and wanted to appeal to your sense of intuition regarding how this kind of works. So the concept that we're approaching is this idea of variability in predictions, meaning if you fit a model, okay, so you have some observed data X, and target value is t, and using that, you fit a model, right? You fit a linear model to this thing. And so for now, we could just think of just a straight line, where we're estimating a straight line based on some values that we've observed. And based on that line that you fit, you're going to use it to make new predictions. Okay? And so what is the value that you would predict? Well, you would take your new x value, you'd multiply it by your slope and intercept estimates. Okay, you would do w hat transpose x new, and this will give you your new predicted value. Okay, so this is your new predicted value. And the question is, how much variance do we have in this new predicted value? Like, how much variance is there? And the solution, if you follow all of the derivations in the textbook, ends up being this. How much variance do we have in the prediction? Meaning, if somebody else were to have gathered data from the same population and fit another linear model, because their observations are subject to randomness, maybe their slope and intercept will be just ever so slightly different, right? So, you fit a line and you say, I think my intercept is this and my slope is this much. Someone else gathers data from the same population and they get a slightly different slope and intercept. Yeah? And so if they have a slightly different slope and intercept and they make a prediction, their prediction is going to be a little bit different from yours. And that's kind of the idea of variation in predictions, right? If I gave everybody here the same assignment, gather data from this population, some random data, and create a linear model, everyone's linear model will be probably similar, but not exactly the same. And then if I say, use your linear model to make a prediction, everyone's predictions will also be a little bit different from each other. Now, how different will those predictions be? Well, it's subject to just how much variation is there in the data itself. That's the sigma squared value. And then the other part depends on x new and x, okay? And it comes in this form x transpose x inverse, and then we're multiplying it by x new on both sides. And this just feels a little bit strange, right? It's like, how do we reason or think about this, okay? But there's almost, it's like taking, this is not quite how matrices work, but you can kind of think of this as having, x new squared. And then this is, of course, we're multiplying by an inverse. It's not the same thing as division, but like if we were just dealing with scalar values, it would be kind of like x new squared divided by x squared, okay? Kind of like that, because we got x transpose x inverse is kind of like x squared. Now, but because it's a matrix, it plays out quite differently. And so let me just show a couple illustrations here. All right, so here, one thing to note is that the y values or the t values don't actually factor into the amount of variation that we have in the prediction. So it really just comes down to how much variance is there kind of inherent to the data, and where your x observations are and where your x new observation is, okay? So this one, we're going to say our observed values, okay? So my x matrix has a column of 1s for the intercept, and this column 1, 2, 99, 100 kind of represents the observed values of x, okay? And so here I'm fitting a straight line where I have values observed at 1, 2, 99, and 100. And then I'm going to make a prediction, my x new, I'm going to make a prediction at 50, where I have it, my x value is 50. Is that okay? So I've got an observation at 1, 2, observations at 99, 100, and my new observation is at 50. And yeah, I have this slide showing kind of what happens here. But maybe I'll draw a little bit on the this board is too far away and it's covered by some of the things. Okay, but anyway, well, if I plug in these things, right? So I've got sigma squared, x transpose new, x transpose x inverse, x new. Okay, let's just say sigma squared is 1. Okay, let's just keep it easy. We'll say sigma squared is 1. All right, so I've got x nu transpose, the inverse of x transpose x times x nu. And when I do this, I get 0.25. All right, 0.25. So this is actually less than sigma squared itself. Okay, so sigma squared is 1. I actually get something even less. And the idea here is, I've got observations at 1, 2, 99, 100, and I'm fitting a linear model here, right? And I've got all of these different colors here. And the idea here is, okay, let's say, I observed these black dots at 1, 2, and these black dots at 99, 100, and I'm going to make a prediction. This is kind of like where my prediction would be, okay, right along this blue line. Now, someone else, because of randomness, maybe they observe values at 1, 2, and values at 99, 100, and when they do, their random observations are just ever so slightly different, right? There's a little bit of noise around 1, a little bit of noise around 2, a little bit of noise around 99, a little bit of noise around 100 regarding the value that they get. And so maybe their line is a little bit different, or, and so this kind of rainbow of lines represents just, again, if I gave you all the assignment of gathering some values at 1, 2, 99, and 100 and fitting a line, everybody might get slightly different lines, and it might look something like this, okay? And when we look at this, a value right here in the middle, x nu being 50, everyone's predictions for 50 probably won't vary too much, okay? In that your values for, the actual values for 1, 2, 99, and 100 are probably going to be more different from each other than your value at 50, because 50 is kind of like in the middle of this thing. Does that kind of make intuitive sense here? So even if your values, one person had high values for 1 and 2, or low values, high values for 9900 or low values for 9900 or something, when you fit the overall line, your predictions for 50 probably kind of around each other. Okay, let's do something similar, but this time we're going to say our observed values are at x is 1, 2, 3, and 4. Okay, so I've got a column of ones for the intercept. I've got 1, 2, 3, 4 for the values of x. And now we're going to, using whatever values I've observed, and again, it's kind of strange to note that y doesn't even factor, but we're going to just say, all right, if I were to use these values, and I'm going to fit a model to the data here, and then we're going to make a prediction for x equal to 100, right? So right away, some red flags should be going off, right? Because one of the things you learn in linear regression is don't use your model to extrapolate out into the future, right? So if you've only observed values for 1, 2, 3, and 4, you can't make predictions for 100, right? It's kind of just like saying, okay, here's a child, we measured their weight at age 1, measured their weight at age 2, measured their weight at age 3, and measured their weight at age 4. The child's getting bigger every single year. Okay, how much is this person going to weigh when they're 100 years old? And we'd say, oh, they're going to weigh, I don't know, 3 tons or something, I don't know, right? Something ridiculous, that just doesn't make sense. And of course, we know we shouldn't be extrapolating and things like that. Even if the linear model is true, we get this wild variation, this variation of 1,901, right? Compare that back to this slide. Our variation for the prediction was 0.25. Over here, the variation of 1,901. What's going on here? Okay, again, assuming that sigma squared is 1. Okay, what's going on here? Well, the picture looks like this, okay? Here, our values are at 1, 2, 3, and 4, okay? Now, again, because the observations we get are subject to randomness, somebody else could get values at 1, 2, 3, and 4. Someone else could get values at 1, 2, 3, and 4. And your slope and intercepts might be quite different from each other because of just randomness. And when you extrapolate all the way out to 100, you're going to have a huge amount of variation as far as what that predicted value could be, right? Somebody could get, when you observe values 1, 2, 3, and 4, perhaps you estimate a slope that's close to 0, right? Maybe there's not a whole lot of variation between x's 1, 2, 3, and 4, and so, your slope is maybe like 0.02, okay? Meanwhile, someone else, because of randomness, their slope could end up being a bit higher, 0.7, okay? Again, just because your range of x values is a lot smaller, and so your slope value could be quite different, and therefore your prediction for where you end up out here could be quite a bit different, and that's reflected here. Intuitively, does that make sense as far as what's going on? Okay, and so and then the same kind of idea, if you were to observe values at 97, 98, 99, 100, and then try to make a prediction at, say, 0, okay, now you get this huge variation as well, 1,940 or something like that. You just get something quite wildly different. All right, before I forget, let me give you your first view quiz answer. What did I set that to be? Okay, the first answer is B. B as in bear. B as in bear. Okay. So that's what we have. All right, so here's something very similar. I've got an observation at 0, an observation at 50, 100, and 101. And then, and how much variation do I have? I get 0.273, right? And because my new observation is going to be at 50, right? So I've got 0, 50, 100, 101, and I have a new observation at 50. How much variation is there for this new observation at 50? It's going to be around 0.273, right? So the idea here is you have an observation, again, 0, 50, 100, 101. And the question is, how much influence does having this point here at 50 have? So what I'm going to do is, if on the next slide, I'm going to cut this one observation at x equal to 50 out, I'm still going to make a prediction at x equal to 50, right? How much influence do you think this one observation has on the variance? So on the next observation, my x matrix is going to be smaller. I'll only have 3 observations. I'm going to have an observation at 0, 100, and 101. And I'm going to make a new prediction at 50. How much do you think the variation here will change drastically or very little? If I cut this one observation at 50 out, I'm going to cut this observation out. What do you think is going to happen? Big change, little change, very little change. What do you think? Anybody? Just a guess, right? You're either going to say big change or little change, and you've got a 50-50 chance of getting it right. What's your gut feeling saying? Little change. Maybe? Okay, well, let's see. All right, so I'm going to cut this out. I'm going to just, basically, on the next slide, everything's going to look exactly the same, except I've cut this one observation out, and we're going to see what effect does it have on the variation on this prediction. Okay, so I cut that observation out. I'm still making a prediction at 50, and it went from around 0.273 to 0.376. Okay, so it went up a little bit. Okay, so it's a little bit bigger, and I get, that makes sense. We basically we're fitting a line on less data. Okay, we're fitting a line only on 3 data points, and so maybe our estimate for the slope isn't going to be as we're not as confident on our estimate of the slope. So there's just a little bit more variation, but the change isn't drastic. The change isn't drastic. Okay, and I don't know what happened to this thing, but the idea here is, okay, here I've got 0, 100, 101. I've got observations here, and we're fitting a line. How much variation is there? I don't know, maybe not a ton. Okay, 0, 100, 101. I don't have any observations at 50. I'm still making a prediction here. And how much variation do we have? It's not, these two pictures don't look very, very, very different. They don't look very, very different. Okay, that's what we have. Okay, what if what if I have a quadratic model? A quadratic model, okay? So I've got an observation. So now my X matrix, and so this is the fascinating thing, right? I could take a quadratic model, and this thing, when I solve it, it still ends up being a scalar value. I have a column for the intercept, a column for x, and a column for x squared. So I've got 0, 0 squared, 50, 50 squared, 100, 100 squared, 101, and 101 squared. Okay. And then I'm going to say I'm going to have a new observation at 50. And when I plug this in, the variance I get is about 1. It's about 1. And frankly, I think that makes, well, there's a good reason for it to be right around 1, and that's partly because, if sigma squared is 1 or whatever, we'd expect this to be 1. Okay, now, what would happen if I remove this data point? So I'm going to do kind of the same thing as I did before. So I have this slide where I've got these 4 observations. One of them, I've got 0, 101, 0, 50, 100, 101. I'm going to make another prediction at 50. What's the variation there? Okay, I'm going to remove that observation at 50. So now I'm going to just have an observation at x is 0, x is 100, x is 101. And I'm going to say, now I want to make a prediction at x equal to 50. What effect do you think this is going to have? Large variation? Okay, and why do you think we're going to have large variation? What's the difference here?
More complex models, so tries to exactly.
Yeah, right. So we're fitting a quadratic model here now. We have a quadratic model, and so yeah, when we end up fitting this thing, look what happens to the variation. It rockets to 1,262. Okay. So with the linear model, removing that one observation at 50, what effect did it have on our predictions at 50? It went from 0.273 to 0.376. Not a huge difference. Over here for the quadratic model, I have this observation at 50. When it's in there, my variation at 50 is around 0.99, around 1. And when I remove that observation at 50, and I say I'm going to make a prediction at 50, now I have a huge variation of 1,262. Okay, so how do we explain just the huge change here? Well, this is kind of my picture. All right, it's wild over here. Okay, so here if I have an observation at 0, 100, and 101, again, there's variation at each of these observations. Then I have an observation at 50, again, variation. But when you try to fit these quadratic models, whatever they are, it might look something, all of these lines might look quite similar to each other. Okay. Now, I have an observation at 0, an observation at 100, and an observation at 101. Okay, and I don't have any observations at x equal to 50. And so when I fit a quadratic model, it could be, any one of these things, right? Depending on what values we get for 100 and 101, and I say, let's fit a quadratic model here, it could end up being like this, any one of these lines in this rainbow here, right? And so if I say, well, I want to make a prediction for x equal to 50, there's a huge amount of variation now, okay? It could be quite all over the place. Because again, we have a quadratic model, and so for values at 0, 100, 101, depending on the amount of the random noise that we get in our data to kind of fit our model, we could end up with any of these fits that are wildly different. Okay, and so this is what ends up getting captured. All right, and it's interesting that kind of sense of variation in the prediction is captured in this expression, okay? And in all of these things we've been assuming that sigma squared is 1, okay? But I think that makes intuitive sense. If your data, if the amount of the data has just a lot of variation, there's going to be a lot of resulting variation. So in all of these things, we've just assumed sigma squared is 1 to kind of emphasize the effect of x that it has. I could have, I guess, shown you more slides where we assume all of the x values remain the same, and what effect does changing sigma squared have, and that's going to increase the variation, but I think in a less interesting way. But it is interesting that what values we have for x and what values we have for x nu play a role here. I guess I didn't make a slide for this, but what if instead of x nu being 50 and 50 squared, what if I plugged in 100 and 100 squared? What do you think would happen here? So if I take the same exact, can I highlight this? Okay. So if I do the same exact thing, except instead of, so if I do this, when you copy from a PDF, some of the symbols change. That's you guys have ran into that, I'm sure, at some point in your R Markdown where it says, like, this symbol is not recognized by LaTeX and I can't do the thing. So, okay. So this is what we have. We have, 1263 here. Okay. If my new observation is at 100, okay, now the amount of variation is just 1. Okay, so quite a difference. And again, if I do it at 101, okay, no change there. If I do it at 99, now we can see there's going to be a little bit more variation. And as I get farther away from these endpoints, okay, the amount of variation gets bigger and bigger. Okay, and again, it's kind of this idea of, right here when it goes through the points, we're expecting it to be in an exact location, but as I get farther away from it, they get bigger. And also, so at 50, we have quite a bit. This is a very big number, but as I get closer to 0, our numbers will start to shrink. Okay, as we're approaching kind of the anchors towards the end here. Okay, so that's again, the book goes through the derivations, and I didn't feel like putting them all up on the slides, but you can read through it, and hopefully these pictures were an appeal to just a little bit of an intuitive sense of what's happening between the relationship between your observed values of x and where you're going to make predictions for x nu. Okay, change of topics and change of gears, I guess. I've been, I thought maybe we'll spend just a little bit of time covering the multivariate normal distribution. I think you've already seen this in 100B, is it? Okay, so this has already shown up and things like that, but we will make use of it quite a bit in future lectures, and so I figure we'll just spend a little bit of time, just a bit of review on this, and if you need to dust off your 100B notes and review the multivariate and normal distribution, do that as well. And so these are just some slides I had written up, and I'm just using them here. Okay, so our regular old normal distribution, the Gaussian distribution. Wait, how many view quiz answers have I given you? Just one. Okay, let me give you your second one, which is E. E as in elephant. E as in elephant. Second view quiz answer. E. Okay, so this is our normal distribution. This is our density, okay? And I don't know if it should be required that you have this thing memorized to graduate as a statistics major or something. No, I mean, You
Chris lets us use notes.
Huh?
So Chris lets us
Yeah,
use
use your notes. You know how to go to Wikipedia, so I guess that's fine, right? It's just like, how do you make a plot in ggplot? I still have to go to Google like all the time to just what is the argument's name? Is I can't remember anything. But anyway, okay. The important thing is anytime you see an e to the negative something squared, okay? So you have e to the negative basically something squared, that's going to have that normal distribution shape. So basically, if you plug in an upside down parabola into the e, you're going to get something that looks like the normal distribution. Okay, so all we're going to do is we're going to take this univariate thing and we're going to say, well, let's make it multidimensional. Okay, let's say we have x now exists in d dimensions. Now, my pictures it's easier for me to think of only like 2 dimensions, but it generalizes to just d dimensions here. So x is some vector that exists in d dimensions. And we're going to say if it's a multivariate normal, x, the vector, comes from a normal distribution where we have the mean mu. The mean mu is a vector of length d. And sigma is a matrix. It's a d by d variance covariance matrix. And your variance for the normal distribution, sigma squared, has to be a positive value, and likewise for the multivariate normal distribution, your sigma matrix has to be a positive definite matrix. Okay, and the formula for the density, like if we wanted to say, okay, what is the we need to get a number. Well, we would do this, and if you look at this, there's a lot of parallels between this and this. All right, it feels quite different, but we have 1 over square root 2 pi sigma squared, and here I've got 1 over square root 2 pi raised to the d dimensions, and then here I have the determinant of sigma. Okay, and then I have e to the basically up over here I've got x minus mu squared divided by 2 sigma, and again sigma squared being our variance. And so, there's no like squaring in vector notation, but basically I've got the same kind of idea, x minus mu transpose times x minus mu. And then there's no division in matrix notation, but over here I'm dividing by the variance, and here I'm multiplying by the inverse of the variance, which is, again, they're like analogs, right? They're not quite the same, but mathematically they're similar, and so we have this thing, right? And then even the negative 1/2 remains, right? E to the negative 1/2, all of this. So I got x minus mu transpose inverse matrix, inverse of sigma x minus mu. Okay, so, and I think I wrote this right. X minus mu transpose is similar to x minus mu squared, and sigma inverse is in the inverse of sigma z. Okay, all right. Oh, and then the determinant. If we forgot about the determinant. Basically, it is the area of the kind of the thing that's traced out by sigma. Okay, but anyway, the role of this thing, this whole constant up here, its purpose, right? Like where did the square root 2 pi sigma squared? Where did all of this show up? The reason why this shows up is because when you take the integral of your normal distribution, it has to integrate to 1. Okay, and similarly, if you take the integral of this multivariate normal density, it's going to integrate to 1, and that's all. Okay, so we're kind of dividing by the area of this thing in order to kind of get it down to 1. So that's what it is. Okay. All right. So here is just an example of the multivariate normal. If your sigma matrix is diagonal, it will just factor out into the product of individual normal distributions. Okay, so here if I have here my mu vector, okay, I've got three-dimensional multivariate normal distribution, but my mu vector is all zeros, and my sigma matrix is the identity matrix, 3 by 3 identity matrix. Well, when I do this, this is going to just factor out into 3 individual normal distributions, okay? Because if I do this, right, the determinant of the identity is 1, and sigma, the inverse of the identity is also the identity. And so if I plug all of this into the density thing, you know, with my mu vectors being 0, I get 1 over root 2 pi raised to the 3rd power, okay? E to the negative this. And if you think about, well, what is x transpose x? In this case, it's just x1 squared, x2 squared plus x3 squared. And when you've got a bunch of exponents added together, you can factor them out into product of exponents. And so this thing just factors out into standard normal, standard normal, standard normal. And so now this is just the result of multiplying 3 standard normal densities together. Okay, and that kind of makes sense, right? So this multivariate thing is just the result of multiplying 3 standard normal distributions, and it's just the joint distribution of all of these things together. Okay, and so yeah, anytime you have a diagonal matrix, it can be factored into a product of univariate normal distributions. Okay? Meaning, you know, when you have a diagonal matrix, you have no covariance between the elements of X. Okay, no covariance between the elements of X, so that can just be factored into individual normal distributions. If you do have covariance between these things, okay, well, now that's when you need the multivariate normal, okay? Now, interestingly enough, is that you can still look at the diagonal, okay, of this thing, and the marginal distributions of each component themselves will be a normal distribution. So if we take a look at just the first component of the x vector, x1, okay, this the mu matrix is has a value of 1 there, and the first element in the sigma matrix is 4, then if we just looked at the distribution of x1 all by itself, it would be equivalent to a normal distribution with mean 1, variance 4. Okay. Similarly, for x2, it would have mean -1, variance 1, and x3 would have mean 2, variance 9. Okay. It's just that if we were to look at these different elements, okay, and say, what is the covariance? What's the covariance of x1 and between x1 and x2? The elements in that vector would have a relationship. You know, x1 and x2 have covariance. X2 and x3 have negative covariance. And in this case, the element here is 0, is the covariance between the first and third elements of the vector, and those would be orthogonal. There's no covariance between them. Okay, so this is just some kind of interesting thing where there is covariance between x1 and x2. There is covariance between x2 and x3, but between x1 and x3, there is no covariance, right? And it's a little bit hard to imagine some kind of scenario where this exists, but there is data between these things. Okay. All right, and so that's what we have. And if you were to kind of subset any of these things, right? So if we were to just make a subset of this vector where we have just the first and third elements, then we can take subsets of this resulting thing, and it would also follow a multivariate normal. So if I just say, all right, let's just delete the middle element of each of these things, well, the resulting vectors, okay, would still follow the normal distribution, multivariate normal, now with mean 1, 2, and this variance matrix 4009. Okay. If you take some kind of vector that follows a multivariate normal distribution, and then you multiply it by a matrix, okay? So kind of like scaling your values, okay? So if you think of multiplying a matrix as kind of just doing some kind of rotation or scaling of the vectors, then the resulting thing will also be normally distributed. Okay, so if we say y is the product of some matrix C times x, then the resulting values y will follow a normal distribution with mean C times mu, and the variance, if you multiply by a constant for a univariate thing, if you multiply by a constant a, then your variance will get multiplied by like a squared, right? And it's kind of like that again, but it's matrix, so it's going to be C variance C transpose to kind of, it's like the effect of squaring this thing, okay? So we're going to say x comes from a normal distribution with mean 1, 2 and variance 1, 0, 0, 3. And we're going to say y is going to be a vector where we add 1 and 2, and we're going to subtract x1 and x2. Okay, so this feels a little bit strange, but we can express y as because it's a linear combination of the variables in x, it can be expressed with some matrix C. So creating this new vector y can be expressed as using multiplying x by C. Okay, so if I do C times x, this first row is 1, 1, and so when I do that, the first element in y is going to be x1 plus x2. And then if the second row in C is 1, negative 1, then the second element in y is going to be x1 minus x2, right? And so you could imagine this, and you could have any other linear combination of elements of x, and you can express that linear combination of elements in x as some kind of matrix operation of C, right? So, I mean, that's kind of the whole idea of linear algebra, is that we're expressing these linear combinations of things with matrices, right? So this is basically some kind of rotation or scale. So I think we're just rotating some of the values in x to get this. Okay, so now y is going to be this. All right, so what is the distribution of y? Well, the distribution of y, or which is this thing, will come from the normal distribution. Its mean is going to be on the top 3, and the mean of the second element is going to be negative 1. And even though x1 and x2 originally had no covariance between them, the resulting values of x1 and x2 and x1 minus x2 now do have some covariance, okay? And so the resulting variance matrix will look like this, okay? So there's the overall variance is 4, but now there's some negative covariance between them. Okay, and I think that covers, okay, and then here's a little bit of a, if you want to get the expected value and the variance of y, here's the derivation for that, okay? So just showing that, yes, indeed, if we wanted to kind of derive how we got that, we can do that here. Okay. Anyway, I'll add these slides to the end of the other slides. So it's a little bit of a, like, two different topics, double feature today, but that will be it. Let me give you your last view quiz answer for today, which is the letter D. D as in dog. D as in dog is our third view quiz answer. Okay, that's all. Have a good weekend. Maybe I'll see you at Data Fest, and enjoy. Other than that, we'll see you I'll either see you later today or maybe on Monday or whenever. We'll see you then.